Hello and welcome to another day of risky business. So to continue where we left off last time, I was playing around with Fedora, and we tried out some Ion stuff from Per Vonson's Bitwise project on the High Five Unleashed. And this guy here gave a follow-up, and I don't know if the person who tweeted me is the same person who wrote the follow-up, but this guy, I take it, is one of the core Fedora people doing the RISC-V work of porting Fedora to RISC-V. And so he had a follow-up regarding directly booting Fedora. Last time we used the change root. But he says, note, you can now run Fedora directly. See the instructions here. And he has two links here. And so I took a look at those. Apparently this one is 404 now. I think he just misspelled it. Yeah. So it's got a bbl.u540. BBL would be the Berkeley bootloader, and the U540 would be the the chip. It's the Freedom Unleashed 540, and I take it this is a Fedora image for the first partition that you can directly boot. And so I've downloaded that on my laptop. I actually downloaded this when I retweeted this back in April 29th, so it's been a while, but I haven't put it on the actual SD card yet. But I did actually get 2 additional SD cards just this month. I got them. They came in recently. I got 2 16 gigabyte micro SD cards. So the one that we already have, we're going to be trying this out on it. We're going to try to directly boot Fedora. And then I'm thinking another one, we can maybe put Debian on it. And then the third one will probably be for whatever we do custom in the future. That's kind of what I'm thinking. So we've got a number of SD cards to play around with, just so that we don't need to, constantly be switching around, reformatting our SD card to whatever we want to be using. But for now, we're going to be using the SD card that came with the High Five Unleashed. And like I say, I haven't actually put this on the on that card yet. So I was thinking about this episode we were going to do that. That's what I was originally thinking. But I actually changed my mind, and there's something else I want to do first. And then after we do that, we're going to try that out. So he has some stuff in this README, and I don't know if this is really relevant, because this part here makes sense to me. It says this bbl.u540 image is for the High Five Unleashed board. It is built from this repository. But then he has these notes here. You must set up an NBD server, see the README file in the GitHub link above, edit the bbl.u540 image, and carefully replace the IP address of the NBD server. Be careful not to make the command line longer or shorter, and then copy the bbl.u540 over the first partition of the SD card. I don't really understand what this is all about. I feel like we probably just need to do the third step, but I'm gonna try that. just copying over the one that we downloaded, and if it doesn't work, I'll look into what all this other nonsense is about. But that's why I wanted to do something first, so that what I'm gonna do today before I try this, because if I break everything on my SD card, I don't know how long it's going to take me to figure out what all this stuff is. So I just want to get something out of the way first. But so here's the other link, which is the GitHub repository, the Fedora RISC-V kernel, and you can see it's the guy who posted this. And yeah, so I'll just go over this README with you guys. This is the Sci5 U540 branch, which contains changes for the Sci5 Hi5 Unleashed U540 board with an NBD-backed root file system. The Linux kernel for the Fedora/RISC-V project, and they link that. This is not the Linux kernel itself, it is the build script and a few patches which we use to build the Linux kernel for the Fedora/RISC-V project. The actual Linux kernel source comes from the following fork, and they link that here. And they say this must be run on an existing Fedora/RISC-V build host or VM. It cannot be cross-compiled. Requirements, you need Fedora/RISC-V, and they link that stuff. Install NBD and handmade-network into the VM environment. Install the kernel dependencies into the VM environment. And they say one way is to run dnf builddep kernel.spec. You must set up an NBD server serving the stage 4 disk image from, and they link that here. And that's the image we put on the second partition. But they're serving this up with the NBD server, and I don't know what an NBD server is. I'm not familiar with this stuff, but they do that. They say, note that this is served on port 10809 by default. You may need to open this port on the firewall. In the makefile, you must set the variable NBD to match your NBD server. Then you build the initramfs as root. So you do sudo make initramfs.cpio.gc. Then you build the kernel with make, and that will give you the bbl.u540 file. So they say the result of doing all this stuff gives you bbl.u540, right? And they say that note we do not use models or modules, test the kernel, get a stage 4 disk image, for example from here, get QEMU system RISC-V64, run make boot stage 4 in QEMU, or you can boot on real hardware. And they say if you do that, you just copy bbl.u540 over the first partition of the SD card, which is why I'm confused about what all this nonsense is, right? If this guy has built a bbl.u540 image, then don't I just need to copy it over the first partition of the SD card, as they say here? I don't understand. So we'll find out when we actually try that stuff. But I wanted to point that out right away, that there was this follow-up to the last episode. So shoutouts to Richard W.M. Jones for that follow-up. That's very helpful, and I look forward to directly booting Fedora on my Hi5 Unleashed. Next order of business. Let's see here. So there was an announcement that Sci5 has been collaborating with Microsemi to create a Hi5 Unleashed expansion board. And so I want to show you guys that. Let's load up the crowd supply page. if it will load. Oh, this is a not the actual crowd supply page. This is just blog, apparently. Do they link it in here? Yes, they do. So this is the High-Five Unleashed expansion board. Pretty expensive, but I did manage to get one purchased. It was difficult, but I managed to get one purchased. But yes, there's this High-Five Unleashed expansion board, and I'll run through what it is. This board is a purpose-built, this board is purpose-built to expand the capabilities of the High-Five Unleashed board, and comes pre-programmed with a PCIe root port and the PolarFire FPGA and much more. Make a RISC-V PC. So basically, it's an expansion board with an FPGA and these peripherals like PCI Express slots, and the FPGA is pre-programmed to do the whatever needs to be done for the PCIe there. And so the idea here is you can just hook this thing up to your High-Five Unleashed, and then you can put a graphics card in that slot, for example, and build an actual RISC-V PC. So again, not really necessarily practical for most people, but it's exciting to see, because when I started this series, RISC-V chips didn't exist, right? Like, there were not actual physical commercially available RISC-V chips at all. And then Sci-5 came along shortly after I had begun putting this series together, and launched their High-Five 1 and the first ever actual RISC-V chips. Now we've got a piece of hardware there from Sci-5 that actually runs Linux, and now we're getting this expansion board so we can build a full-blown PC. So it's pretty incredible when you think, I mean, I've been doing this series for like a year and some change or something, and it's already progressed this far. So amazing work from Sci-5 especially, and now Microsemi as well. I'm very impressed with how far it's come along in such a short period of time. Like, my series can't keep up. There's still tons to do with the High-Five 1, and now we're playing around with the High-Five Unleashed as well, which has kind of become the top priority for now. And yeah, and so I'm going to be building a RISC-V PC for this series. I think that's going to be a lot of fun. We're going to do, we're going to get this expansion board, hook it up to the High-Five Unleashed, and we're going to build a custom case for it, I think. And we're going to, see if we can fill it up with some stuff like a graphics card, and whatever else we need, and get an actual nice little PC going. I think that would be a lot of fun for the series, as well as something that's really nice that I could take, if there are future handmade cons or other, events that I go to like that. It would be nice to be able to, have something to actually demo to people that show up to a conference or something like that. So I think that's a really exciting idea there. Like what Sci-5 is already doing with their stuff. But then, just to go over it a bit, they give the dimensions here. It says it comes with a power supply, USB cable, and an FPGA programmer. It comes pre-programmed with a chip link to PCIe root part bridge enabling easy connectivity to PCIe add-in cards. The board also has additional expansion capabilities for bit streams yet to come, so exciting things to come down the line with this board too, that you know, the hardware is there, it's just enabling it in the FPGA essentially. So it says it's 300K logic element, low power polar fire FPGA, 24 lane PCIe switch, one PCI Express card connector, an X16 or an X1 PCI Express and an X16 PCI Express card connector with 4 lanes of PCIe Gen 2 connected, an SSD M.2 connector, a SATA connector, an HDMI connector, an eMMC NAND flash, USD card slot, micro SD card slot, USB to UART bridges, 4 gigabit DDR4 X16, SPI flash for remote FPGA updates, QSPI flash connected to GPIO, 2 CAN transceivers, FMC, is that FMC? Yes, FMC. Connection to HFU 540-4A00 kit. So that's an overview of what this thing's got on it. And they say use cases, build a RISC-V PC, add a graphics card, hard disk drive, or PCIe USB card for keyboard and mouse. Use a Linux development workstation. Port your favorite packages. So, you know, we're definitely going to be doing porting. Like I say, I want to do a stream from the Hi5 Unleashed. So all the packages we need might already be ported, because it seems like a lot of good work has already been done in that regard from the, you know, the distro maintainers of like Debian and Fedora and stuff. But we'll see what's out there and what we might need to potentially port ourselves. We're definitely going to be using it as a Linux development workstation in some regard. I mean, it's not going to replace my streaming setup that I have here yet, but you know, it's definitely going to, you know, we're gonna play around with it a fair bit. And yeah, I mean, we're gonna want to add all this sort of stuff to it and build a RISC-V PC. So yeah, I'm pretty excited about that. So there's definitely a lot of exciting things to come when it comes to the Hi5 Unleashed and what I'm going to be doing with it on the series. And here you can see a picture of the expansion board connected to the Hi5 Unleashed. So, you know, a little bit of a scale comparison. You can see this right here on the right is your Hi5 Unleashed, and this big honking thing over here is your expansion board. So that's the hardware we're going to be working with. So I'm very excited about that. So that is the big news. Let's continue here in the Twitter feed. So another thing that's not really related to this series, but I switched to using Cubes OS on my laptop, and I won't go too much into detail here, but overall I'd say I've been using it for quite a while now, and I like it. It's not perfect. There are plenty of things I have to complain about with it, but for my use case, it's pretty good for what I do with my laptop. I wouldn't use it on like my workstation or anything like that, but for a laptop, I'm quite happy with it. Let's see here. So yeah, I managed to get the expansion board purchased. Also, in case you don't know, back in May 27th, I take it Godbolt didn't have any RISC-V targets. Just recently, I saw Pervanson using it, and it has a Clang RISC-V target on it now, but it still doesn't have GCC, interestingly. But I added a compiler explorer to links.risky.tv, and it's this link right here, which is off the top of my head, I don't know who it is, but I believe it's someone who works at Sci5 who has this up. His name is Michael, I take it. But yeah, I don't know for sure who this is, but they have a compiler explorer up. And I don't think compiler explorer really works in Pale Moon, which is the browser I'm using here. So I don't know if this will even load. But anyway, that's there. So if you can get it to load and work in your browser, it's worth checking out. I don't know why it's not loading though. I mean, I don't expect it to work in Pale Moon, but it would be nice if it actually loaded so I could show you, but yeah, I just thought I'd point that out. So if you go to links.risky.tv, and if you go to software here, first link, compiler explorer, that's what I'm talking about here. And so that's a useful thing to have handy. And I thought I'd mention that because it came up just today actually. Oh, and I also posted questions on the Big Risky Business thread. We'll get back to this in a little bit. Let's continue, just going in chronological order here. So the Big Risky Business question thread, I've asked about what people are using at Sci5 for hardware, and we got an answer from Jim Wilson at Sci5. He says, if you look at the Sci5 Freedom USDK project on GitHub and look at the conf/Linux buffer SMP file, you'll see that it enables Radeon support. Looks like an HD 6450 in one of our demo boards. So I looked up the HD 6450 and it's a pretty cheap low-end card, but that's what they're using for their demos. So I'll probably go with the same card just because we know it works for them. So it seems like a nice way to go. I don't really want to get into trying to port drivers for a graphics card to this thing right away, right off the bat. That could be interesting to do at some point, but that's definitely not a priority for me. I just want to have basically a demo machine like Sci5 has is pretty much what I want my my RISC-V PC to be, essentially. And so I'll probably go with one of these cards, and also because just of the expense, I've already poured a lot of money into this project, and a cheap card would be nice for my wallet. So there's that consideration too. And then he says, I don't know if anyone has tried Freedom ESDK. Oh yeah, that's the other thing I asked. I was wondering if anyone has run the Freedom ESDK on a RISC-V host. So like if you ran the Freedom ESDK on the Hi5 Unleashed and then used the Hi5 Unleashed, your Hi5 Unleashed PC, to program your Hi5 1 like we currently do on the series with our x86 workstation. And He says, I don't know if anyone has tried FreedomE SDK on a RISC-V host, but I would expect it to work if you have enough free USB parts. It is just Linux software and should compile fine on a RISC-V Linux machine. So that's pretty interesting. I would have expected that there would be specifics like inline assembly type of things that would need to be ported over, but it sounds like there's nothing too specific to x86 in the SDK. So that's one thing I definitely want to try. I want to try to, actually be able to work with our Hi-Fi 1 from our RISC-V PC that we're going to build. I think that will be a fun project. So let me log in here quick so that I can part his post. All right, now the next piece of news is that GitHub was acquired by Microsoft, and I have a policy of not using anything by Microsoft. I haven't in many years. The only exception is at my previous job, I needed to develop software for Windows, so I had a Windows VM that I pirated, of course. But in general, I do not use anything from Microsoft, and if Microsoft acquires a company, I'll stop using the things that company developed. So I no longer am using GitHub. I deleted my GitHub account entirely. So as a result, the Risky Business GitHub no longer exists, but I moved everything over to GitLab. So, or I guess I already have it open. You can see right here we have a Risky Business GitLab, and everything is on here. I still need to update my remotes. I just did the annotations one today, but I still need to update my my remotes in my local repositories for all these. But we'll do that as we use them. I also tweet when I go live now on Twitch. I mentioned that in a recent book club episode. I did a poll on it. It only got 3 votes, but 2 out of 3 said yes, so that's what I'm going with. If people complain loud enough, I might change my mind about that, but for now, that's what we're doing. Midlo has also created this amazing episode guide. So the actual guide is a secret link, but this is just the landing page for it. And yeah, it's really great stuff. It's early access for anyone who backs me $1 or more on Patreon or Gumroad. You get access to you already get access to early access to my videos 1 week before they get published publicly. But now you also get access to annotations as soon as they go live on here. So if you like to use the episode guide and you're a supporter, you now have early access to that too. And honestly, I like this site better than the one that's on handmade-network. I mean, let's just, since I have Bitwise open here. Well, I guess it's not a good example. So let's go to sonera.risky.tv, which takes us to the episode guide for Risky Business. I think the topics on here, and I'm sure Miblo could fix all this stuff, or whoever, the people at Handmade Network, I'm sure they could improve this stuff. But so we have like RISC, book, RISCY. The RISC one is the miscellaneous, and Miblo is calling it RISCalaneous. And so that one's just called RISC, but I think that's kind of confusing. It would be nice if that actually said like RISCalaneous or miscellaneous, so it was clearer what that actually is. And then for the book one, it doesn't have subcategories, so all the co-ed episodes are in here, but then all the RISC-V reader ones are in here too, and they're kind of confusingly placed, like or like this is like day ER001, and it's a lot nicer in the private episode guide. So I actually like personally, I actually prefer the private one over the public one, honestly. And it's a cool site. It's just a really nice site. Miblo's done amazing work on it, and it's got really cool. He looked into getting nice fonts for this stuff and has formatted it very beautifully. So I'm very happy about that. And then he also went above and beyond, and he made this logo for us. I didn't even ask for a logo. Like, I never mentioned anything about a logo to him at all, and he just sent this to me. He was like, "Hey, I made a logo." So yeah, we've got a nice logo, and it's perfect for like avatars for sites like Twitter and everything else. All of the social media and various platforms that Risky Business exists, we're kind of spread out among various platforms rather than having one unified thing that we made ourselves. We're just existing on top of other sites' infrastructure. So as a result, we have plenty of accounts that need avatars, and now we can actually have something that's kind of branded, so to speak. So that's pretty cool. There's also a new series that you might want to check out. Someone named Sam Alvo has a new series where he's building a RISC-V system, I take it, and he's calling it the Kestrel Computer Project, and it's RISC-V based. And like I say, it's going to be a video series, so he's done an introduction episode already. So that might be worth checking out. I added that to links.risky.tv as well. And the other thing to mention was going back to the Godbolt stuff, the compiler explorer. So there's this thread here. Per Vonson noted that he wasn't able to get the GCC RISC-V backend to generate jump tables for switch statements, and he linked to Godbolt, and it actually has a RISC-V target. So here you can see, well, okay, it's not going to load. Probably because Pale Moon. But let me just see if I can put it in Chromium. So let's copy this link. Yeah, so here you can see it has a RISC-V 32 bits Clang target. It's RB32G that they're using. And yeah, and then the other one that I showed you that's on links.risky.tv has GCC targets. It's more feature rich in terms of RISC-V support. But so I told him, you know, I CC'd Palmer from Sci5 because I know he's maintaining all that stuff, and he chimed in some helpful information. He noted that it's the LLVM part, not the GCC part, that's on Godbolt. He also was able to get it to emit what Per was asking about and had some comments on that. He also mentioned down here that there is a GitHub issue open for GCC in Compiler Explorer. And so that's what that's talking about is the Godbolt. There's a GitHub issue open to add GCC RISC-V targets on there. And it has a link in the comments on that issue to Michael's server, which is the one I was talking about. And so that's where I found it, actually, is through that GitHub issue, because I was wondering why Godbolt doesn't have GCC RISC-V targets. And so I found that and put it on links.risky.tv. So I mentioned that here as well. I just thought I'd point that out because that discussion was just today. So that's useful to know. And with that, we're caught up on all the news. It's been a while since the last episode, so there was a fair amount to go through. But with that said, let's jump into what I want to actually do today, which is I have this Hula repository, and in case you don't know, I detailed what this is in the first episode of the Bitwise homework that I do, which you can find on my YouTube channel. It's not annotated, but I have this example of what the language is going to be like, or what I'd like it to be like at least. And it's just a hello world that runs on RISC-V Linux. And it's pretty straightforward. And I've translated that into assembly, hand translated. And this is something to note too, that Per Vanssen recently went over looking at constructs in C and how you would translate those to assembly by hand. But it's also useful if you're trying to implement actual like code generation in your compiler or something. But he went over all that stuff on his Bitwise series, which I highly recommend checking out. But this was done before that was done. So hopefully I didn't commit any terrible mistakes in my assembly. But I just did this from my own understanding of assembly and using like the RISC-V reader as a reference, as well as the Linux source tree and the posts on the mailing list when Palmer actually submitted the patches for Linux support. That was the only place I could actually find proper documentation of the Linux ABI for RISC-V. So hopefully that gets documented better at some point, but this is what I came up with for the Hello World program. And so what I'm thinking is, now that we have a RISC-V Linux system that we can actually, an actual real hardware that we can work on, we might as well try actually writing this program in the Fedora environment, like actually write the file in Vim, and then compile it, or assemble it, I should say, and link it and see if it will actually run, and then debug all of our terrible errors that we have probably committed here, and so we can actually test this. And so that's what I want to do, is I want to actually test some actual assembly. Let me turn on my High-Five Unleashed, and we'll jump into this here. I'll put on my anti-static wristband here. Alright, I am now grounded. Now we're going to plug in the High-Five Unleashed. And let's try powering it on. Alright, and there we get the heartbeat. So we should be good to go. Let me close Compiler Explorer for now. And this is a great example of the kind of tooling work that we're going to be doing on this series, by the way. We're definitely going to have this type of thing in our tool chain. But not as a web application, of course, as a proper application built from scratch for a desktop system. So what all do I have open right now? Looks like this one would be the one to go with. So we're going to connect to it with screen. All right, what is it? Root sci 5, I think? Yeah. Let's run screen inside of screen. And we're going to, in this one, how do we do this? We just say ps1 equals, right? It's just a bash variable, I think. And we're going to want to say this one is the default environment. What is it? BusyBox? And then this one, we're going to mount that. And then we're going to do a change root. and then we're going to set the PS1 equal to Fedora. So this was a suggestion from Miblo to set the PS1. So now you can see you can easily see what I'm in when I'm switching between stuff in screen. So here it's clear that I'm in Fedora because it says I'm in Fedora. Whereas here I'm in BusyBox. So that should make it easier to follow along. So here in Fedora, what we're going to do, head on over to our root home, and then we're going to start writing a hello.s. So I thought we had Vim. Is it just VI that we have? Okay, well then we're going to write it in VI. And we also have this problem of it not seeing the screen height properly, but we're just going to live with that today. So here's the program. Here, can I put this, just open this raw. And then maybe increase the font size some. That looks pretty good, I think. So this is what we're working with. And then I'm also we're going to go over the program since we're going to actually be working on this program. And I'll show you guys how I wrote this basically. So first of all, let me open up a terminal on my normal system. And we're going to open this raw, select all, copy. So here's the program, and we're going to go over how this is written. So basically, the first thing you need in any program is your entry point, which is going to be start. And so we're going to have, what we're going to do is we're just going to set it up to call a main function like you do in C. So in C, you normally just write your main function and the start is provided for you unless you're writing your program from scratch. But if you're writing it from scratch, you need to provide the start. And what it does is it takes, it doesn't take any input, but it outputs this assembly block, is just going to output argc and argv. So we're parsing our argc and argv from the stack basically, and it clobbers a few registers and memory in the process. So what you need to do is you need to zero out the frame pointer, which is the I'm following the C ABI here. So this is what you do. You're expected to do at the start of a program. You're expected to set the frame pointer to 0. Technically, we don't actually have to do this because we're not using the frame pointer, but we're just following the C ABI here. The next thing we're doing is we're loading a word from the top of the stack to A0, and then we're adding 4 to the stack. Next we're doing, and remember the stack grows down, right? So that's popping off the stack, and then we're moving the stack pointer, the current stack pointer after we've popped that off the stack, into A1, and then we're aligning the stack pointer to a 16 byte boundary, which is what this is doing here. And this is like a common trick that you see to do this. Basically, this -16 translates to, in 2's complement, it's like, 0x, bunch of f's, and then the last one is 0, basically. And so by anding that, you're just you're zeroing out the bottom nibble, which aligns you to a 16-byte boundary. Once we've done that, for a basic program like this, that's all we need to do. So then we're just calling main with argc and argv, putting that in return variable here, and then we're calling exit with the return variable. And exit, of course, is a Linux system call. So, and again, like the way this works is what this syntax is saying, and I just made up the syntax, but what we're saying here is that argc, this variable argc, is going to get filled in with the value from A0 after this assembly block. So if argc wasn't already A0, it would need to move it, like move whatever, you would need to move A0 into whatever register argc is. But I've explicitly annotated this, that argc should be A0 and that argv should be A1. So what this syntax is saying is that this variable is A0, the register A0. This is the register A1. So what we're saying here is, after you do this assembly block, move A0 into argc, move A1 into argv. Well, these are already those registers, so you don't actually need to do anything, right? So this means there's nothing you need to do to get those registers into the variables argc and argv. It's just you do this assembly code, and then it's set up so that when you do this function call, it works, right? Yeah, that's how this works. The other thing is, once you've written this much, the thing is, now you need to define exit, because exit is not, of course, defined for you. So what you need to do is you need to write an exit function, and you just give the signature from doing man to exit, and you can see the signature for it. And it also will tell you, helpfully, that exit, the glibc exit, is actually a wrapper for exit group. You can see that right here, C library / kernel differences. Those are the kind of things you want to watch out for when you're reading man pages about system calls. Is you want to know what the C library is doing that is different from what the kernel actually does. So the C library is actually using the exit group system call to do an exit. And so it doesn't really matter for us, because that has more to do with like threading. Like if we do man to exit group, this system call is equivalent to the exit system call, except that it terminates not only the calling thread, but all threads in the calling process's thread group. Well, it doesn't matter to us because we're not doing threading, right? But I just am going to use this anyway because there's no reason not to. So it makes sense to use the proper the proper thing that would be used normally. So that's what we're going to do to implement exit. Is we're going to do an exit group system call, and we can see that we just take an integer for the status and we return void, and it's also no return because exit is no return, which they don't make explicit here, but it is obviously because it's the exit of the program. So what I did in this is I marked it like the return type as no return. In languages like C, what they do is they have this as like an annotation and you mark it as returning void. But to me, I think why not just have it as the return type? And maybe that will become apparent when we implement the actual language, but I feel like it would make sense to have no return be an actual return type, right? Like, it's not that you're returning void, it's that you're not returning at all. The function doesn't return, right? So it seems like you should have that in the signature. That's just the way I think about it. But anyway, I also mark it as naked, which means that it doesn't generate the function prolog and epilog that functions normally have. It's just literally just the stuff that's in the body is what is going to get generated for this. And so what's in the body? Well, it's some inline assembly. It's just an scall instruction, which is the RISC-V instruction for doing a system call. And the ABI is that you put the system call number in A7. And so what you need to do is you need to look up what the system call number is for your architecture in the Linux source code, the Linux kernel source code, and you need to look up the you need to look up the ABI for your architecture. And like I said, if you want to see the ABI for the architecture, the best way I've found to do that so far is Palmer Linux mailing, maybe? I don't know what to search for here. Pull request for Linux Next. Okay, so I think this is the one. So if you read through this stuff, I don't know if he details it in all the text up here. I don't remember, but if you look, I think what I did is I just looked through the actual. Oh, maybe this isn't the one. I looked through the actual diffs. So let's maybe check this link. No. Let's say Palmer Linux patch. So probably maybe I should probably put it in the links.risky.tv when I find it because it's maybe not so easy to find what I'm thinking of. So maybe Oh, nice. Yeah. Do this CAPTCHA. Type what that says. Uh-huh. I guess maybe we can see it on the mirror? So let's see if we can find his initial RISC-V work in here. I might have to find what I'm thinking of off stream sometime and then show you guys the next episode when I have the link, rather than wasting all the time here trying to find it. So I think we're gonna give up on trying to find it right now. But for now, you're just gonna have to take my word for it that we put the syscall in A7, and then A0 and up are the arguments to the system call. And so what we're doing is we're saying put 94 in A7, put status, which is the input to the exit, into A0, and that should already be in A0 because that's our calling convention. So that won't actually do anything. It's just doing a load immediate here, putting 94 in A7, and then it's doing an scall, and we're saying it doesn't output anything but clobbers memory. So that's how we implemented exit here. And then the other thing to point out is, where do you find the system call numbers? And I can't guarantee that I have them right, but these are the numbers I found. And if we just go to the Linux source tree, and is it under include? I don't remember. I think it's what I found was the ASM generic, that RISC-V uses the generic stuff, and they have the syscalls in here. So if you go to one of these, is it syscall.h? Let's open both of them. No, not this one. So this one right here, the syscall.h in ASM generic. If you look through here, oh, maybe that's not what I was thinking of. Where's the actual... Is it under bitops? Okay, let me go back to syscall.h and read what they said in this comment here. I don't think it's UniSTD. Is it export.h? No. Somewhere there are syscall definitions. I think it's this stuff here in the UAPI ASM generic UniSTD.h. Yeah, it says this file contains the system call numbers. It says new architectures should use this file and implement the less featureful calls in user space. So I take it that RISC-V, since it's a new architecture, should be using this. And if we search exits, we see exit group is defined to be 94. So that's where I got that system call number. So at least we were able to find that today. But so that's how you implement exit. And then the thing is, now we want to actually write our main function. And so we go in here, and it's your typical main signature. It takes argc and argv, and it returns int. And so we have a constant. That's just the string hello world. And then we set a pointer to that, and we get the length of it using size of and subtracting 1 from it because it's null terminated. And then we do a loop. And the reason we're doing a loop is because essentially what you would initially write is you would just do, you know, like write std out file no hello len, and in practice oftentimes this is what you'll do, is you'll just do the write and not bother about looping. But if you actually look at what write does, basically on success the number of bytes written is returned. And it's not an error if the number is smaller than the number of bytes requested. This may happen, for example, because the disk device was filled. See also notes. So basically, you can get a few different cases where this might happen. So you can get E again in the case that it's non-blocking and the write would block. You can get E would block as well. And you can also get E interrupts if the call was interrupted by a signal before any data was written. So there are a few different cases that you want to handle, and you just want to loop over trying to write until you've written everything there is to write, basically. So you do an infinite loop, and then you say you try to write it. If it is if it's greater than or equal to 0, that means we actually successfully wrote some stuff. I mean, unless it's 0, but we don't really do anything special for that case. I guess you could, but we're not. So we just say hello equals hello plus ret. So what we're doing is we're advancing the pointer by the amount we wrote, and then we say the length is equal to the hello length minus how much we wrote. And then if our hello length is 0, that means we've written everything, so we break out of the infinite loop. But if the return value is less than 0, that means it's negative. We check if ret is equal to E again, E interrupt, or E would block, and I define those to be negative, whereas these defines would normally in C be positive, right? Because they're Erno values. But Erno is stupid, so we're not using Erno. We're just directly using the negative version, which is what the kernel returns, which is the proper thing to use, in my opinion. So we just check if it's any of those. If it is, we just continue, which means we're just going to loop again, try again, and then otherwise, if we got a different error, then we failed to write in a non-recoverable way, so we're just going to exit with the return code. And then once we're done, we do a return 0 at the end to signal success, that the program finished properly. So that's how that works. It's pretty simple, and again, the way you do this is you just look up how do you do a write in Linux, right? How do you print to the terminal in Linux? And if you've got the Linux book like I do, that's you just look it up in there, and I'll tell you, if you don't already know that you use the write system call with std out file no. And you find the defines for this stuff on your system, or you can look in like the muscle source code, for example. I think that's where I pulled these values from. But it doesn't really matter where you find them as long as you get the stuff you need. So yeah, I define these, and it turns out that on Linux, E would block is the same as E again, but just for completeness sake, I check both of them, even though it's a duplicate check. And in practice, for something like a hello world, you probably wouldn't need to worry about E again or E would block, because it's not like we're writing to a non-blocking socket. But anyway, this is how I implemented it, and I think it's a pretty decent example of a hello world and shows off features of the language pretty well. So the only missing piece here is how do you implement write, and again, it's the same way you implement any other system call. You just, implement a wrapper to the system call. You need a result this time, which is going to go in A0. A7 is going to be 64, and I already showed you how you find that system call number. And then for input, you're taking your file descriptor, your buffer, Your count, like I say, your results is A0. This clobbers memory, which all system calls do. And then you do scall. And then you just return the result. So it's pretty simple. And that's the entirety of your Hello World program there. Now, when we look at the source code here, you'll find that it's a very straightforward translation, and essentially all you need to do really is look at this and then just go through and start translating stuff. So the first thing I said we do is we define our start, and so we're going to go over to our Fedora environment with our VI, and we're going to define a start. So let's see the syntax we use here. So we need this to be in the text section. We need to align it to which I think is the same as be aligned for, like a 4-byte boundary, if I remember correctly. Don't quote me on that. But the text section needs to be aligned like that. And then the global start, so that's your symbol, and then we have a label for it as well. So let's start by typing that stuff in. And again, for the specifics of this stuff, of like, okay, you need to align this too, you can find that in the RISC-V reader. It's a great reference for this stuff. It had a lot of useful stuff in there, and it defines what all this stuff does, and you can also look up the documentation for the GNU assembler, which I have linked in links.risky.tv. But let's just start typing this stuff. So we're going to do .text, and we're going to do align to, and we're going to call this start, and then here's our label, and let's start writing some code. So the first thing we need to do, let's just switch over to our code here. So we see the first thing we need to do is we need to zero out the frame pointer. So that's going to be like this. Next thing we're going to need to do is we're going to need to load A0 with the top of the stack, and then we pop it off. So because that's an integer, it's 4 bytes, which is why there's a 4 there. And then we need to move the stack pointer into A1, and we need to align it to a 16-byte boundary, align the stack. And now that we've done that, we're ready to call main. So we're going to do call, and this is a pseudo instruction, but we're going to use it. I believe the GNU assembler should support it. So we're just going to do a call, and we're going to say call main. And then once we're done with that, we're just going to say call exits. And I think that should be good. Let's reference our assembly and see if we missed anything. No, this is how we wrote it in here too, so that's probably good. Probably a good sign. Okay, next up, let's do exit because that's the logical thing to do next. So we're going to say so that's what that line is actually saying. I got overridden by a message from the system. So we're going to have a global called exit. And we're going to create a label here. And what is exit going to do? It's going to load, what was it, 94? Is this call? Yeah, 94 into A7. Scall ret. I believe that's everything it should need to do. Let's take a look and see what we actually wrote in the assembly file. Oh right, we don't need a ret because it's exit. Duh. No return. So we do that. What else? So the next thing we're going to do is do main, I think. So let's do main here. And we're going to say, let's see, what do we need to do in main? Oh yeah, so we're going to want a constant for hello world. So that actually needs to go in its own section. Let's refresh this. Okay, so we're going to say, and it goes in the data section. So we say .ro data, and then we do be aligned for, because that's how it's to be aligned. And one trick I see people do often in assembly to get the size of a string is they'll put a member in the data section after the string and do pointer arithmetic, basically, where they take the current address that you're at and you subtract the address of the label for hello, and that'll give you the length of the string, right? But you can't do that if you are aligning to a 4-byte boundary, because then there's potentially padding at the end of this, which is going to throw off your calculation. So I believe you're supposed to do the alignment. I mean, strictly speaking, you don't need to. There's plenty of stuff in here that you don't strictly need to do, like I mentioned, the frame pointer, for example. But you know, and like, you don't need to be doing this check. You can probably even get rid of this check. You know, you maybe don't even really need to be looping here. But we're gonna go ahead and align it like you would do in a C program, compiled down to assembly. So we're gonna go here and start the data section, read-only data section, and we're going to say be aligned. And I don't know why be aligned versus align. They're just kind of like two ways to do the same thing. And this is how they did it in a Hello World example given in the RISC-V reader. They actually did an align for the text section and a be align for the data section. Don't ask me why, because I don't know. but we're gonna follow that convention just because that's what they did. And yeah, then we're just gonna have our string. So we're gonna have a label, and then we're going to say .string, and this directive creates a null terminated string like in C. So that should be good like that. And with that out of the way, let's see what else we need to do in here. So we need to have a hello variable, and it's going to point to the constant. So the way we're going to do that is, well, first of all, let me make sure this is refreshed. Let me go into main here. And so the first question is, what register are we going to put it in? And so I'm going to use an A register, because why not? So we used A0 and A1 already for RISC-C and RISC-V. So let's put it in A2. And what are the instructions we need to do? We need to do a couple instructions, although I think there's a pseudo instruction for this. I think there's like load address. Something like this. Let me see what it is in the code I've written here. Oh, so I actually did it using the LUI add-I pair. So let's do that then. And I think the LA is if you want it to be position independent, actually, now that I think about that. And again, you can look this stuff up in the RISC-V reader. That's the best reference I've seen for this sort of thing. So the upper immediate is going to be the high part of hello. And then we need to add in the low. So I think that should be good. Let me see what we did here. So we used a saved register, but we'll get to that when we actually see why we need a saved register. But yeah, we do %high here, %low here. Seems good. Let's continue on here. So next thing we need to do is the size of, and this is the case where, like I say, because we're aligning this, I don't want to do the calculation in the assembly code because I think it will be wrong from padding, or potentially wrong depending on the size of the string. So we're actually going to count it by hand. So if we do this, I'll go one back because that's 2 characters to represent 1 character. Oh, VI doesn't actually show you. Okay, so we actually need to count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then the 14th would be the null terminator, right? Let me double check that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh, I forgot an exclamation mark. That makes it 14. So we're going to put that in, I guess, A3. So load immediate A3, and we're just going to put 14 in there as the length of the string. Although, so we've got these in registers, but the next thing we need to do is we're going to need to actually write it. And so there's going to be a loop here. So I'm just going to do a label. And the first instruction is going to be call write. And so now let's take a moment and define write. So we're going to load an immediate A7, and what's the system call number? 64. And I think everything else should be in the right place. So our signature FD is A0, buff is A1, count is A2, and that's what we're passing into it. So yeah, we should be able to just do an scall now, and then we're going to actually need to do a ret, because it, you know, it's actually going to require a ret. So there's our write. The next thing we're going to need to do is branch greater than or equal to 0. And so we're going to do A0, and we're going to branch to looking forward. Now in here, we're going to do hello equals hello plus ret. So hello is what we're currently calling oh, and the other thing is this needs to be, so hello should be the first, or hello should be in A1. This should be in A2, and we're going to need the system call number in A0, which is I mean not the system call number, the file descriptor, which is going to be 1. And see, the thing about doing this is if you put them in these registers, now when you call write, according to the ABI, like in actuality, we know the machine isn't going to clobber these because we know we're just doing a write call. But if you're following the ABI, you can't assume the values are preserved after the call. So, you know, if it was a compiler generating this code, it wouldn't be able to make that assumption. And so you need you need to actually put these in saved registers. So let's put this first one in saved register 0 because we're going to need it. And can we use saved register 0? I did in here. I don't know if we want to actually use S0 because S0 doubles as something else. I think it's the thread pointer though that it doubles as, and that doesn't matter to us. So yeah. So these should be S0, and then we want to keep this around too, so we're going to put that in S1. The system call number we don't care about, or I mean the file descriptor we don't care about. So that we're just going to put in A0, and then we're going to move S0 into A1 and move S1 into A2. So that puts the pointer and the length into the second and third arguments to the function. And then what do we do next? So we say if it's not, if hello length is 0, break. So we're going to do branch it should be if it's just equal to 0. So I believe that would be BEZ, right? Branch equal to 0. So or wait, we just did the call to write, and then we did this check. So in here, we need to do hello equals hello plus ret. So we're going to say S0 or add S0, which is the hello pointer. And we're going to add S0 and the return value, which is A0. But yeah, that's good. And then we're going to do a subtraction, which is actually just an add, but they have a pseudo instruction for it, I believe. So S1, S1, and then A0 again. And now we're going to branch if equal to 0. We break out of the loop. So I'm just going to call that 3. Okay, next we get to the else if, which is the 2 label. And so we need to check if the return is equal to E again, if it's equal to E interrupt, or if it's equal to E would block. So first thing we're going to need to do is load the immediate. So I'm just going to put this in a temp register. Okay, so we've got E again, which is -11. And then we're going to say branch how do you do a branch equals? I guess it's just BEQ. And what is the... Okay, it is BEZ. I was wondering about that one. That needs an F on it. Okay, so the else is what we're going to be branching to. So this should actually go to 4. This is where the else is going to live. Next number is -4. And then we do 11 again. Which again is not necessary, but we're doing it for completeness sake. Or those are actually supposed to branch to the start of the loop, so those need to actually go to 1b. And I'd like to continue, but I'm feeling a little off and tired, so I'm actually going to call it here, and we'll continue in the next episode. So thank you everyone who tuned in today, and thank you everyone who watches on YouTube Archive, which is available at RISCY.tv. And you can follow me at HMN_RISCY on Twitter to get updates about the series. Thank you also to everyone who supports me on Patreon at patreon.risky.tv. It makes this series possible. I don't have new shoutouts to do right now. And I'll see you guys in the next episode. Stay risky, everyone.